Hello, everybody. Welcome to today's current seminar. Today we have one speaker, one talk. Our speaker is Samuel Grauer. He will be giving a talk on reconstructing turbulent multi-phase flow states from inertial particle tracks. Samuel Grauer is an assistant professor in the Department of Mechanical Engineering at Penn State. His research group studies inverse problems related to optical diagnostics. This work involves data assimilation for flow reconstruction, limited data, non-destructive testing and evaluation, and large-scale nonlinear uncertainty quantification. With that short introduction, the floor is yours, and you can start your presentation.
All right. Thank you very much. Thanks for having me. I'm really excited to chat with you guys today about this. So yeah, we use a variety of data simulation methods in my group, but one of the things we're really interested in is pins and trying to push the boundaries of what you can do with pins, and especially, as my title indicates here, in the context of dispersed multi-phase flows in cases where you've got inertial particle transport and also in multi-phase problems where you've got a fluid structure interaction. So before I say anything else, I have to acknowledge my group who does excellent work, and it's a pleasure to work with all of them here at Penn State. And particularly with respect to the work I'll show today, I have a student, Joe Molnar, Ree Tang, and Ko Jo, who've done most of the work. And really, this is largely Ko's work. So all credit goes to them. Sorry, just got to close that out there. All right. So with that, what I'll talk today about is related to a measurement technique called Lagrangian particle tracking. And I'm going to start by introducing that method and describing why we do it. And throughout the talk, I'll get into some of the complexities that LPT brings with it and why we need to think hard about the details of Lagrangian particle tracking if we want to use a pin for reconstruction. So to start off with, many flows in nature are turbulent and also in engineering devices. And we want to be able to utilize turbulence for our benefit or mitigate it in cases where it has adverse effects. So maybe we want to keep a boundary layer attached. And so we want a turbulent boundary layer to entrain momentum. We might want to promote mixing. We could also be trying to fight off drag and mitigate turbulence or reduce it or reduce noise. And so the question is, why can't we just use simulations? Why would we need to do something like Lagrangian particle tracking at all? And many flows are challenging to simulate. So that's going to be the crux of the answer. This is especially true if you don't know the boundary conditions. So I might have a flow where the area of interest from an engineering device, the flow in that area couples to a very large system. And I can't resolve the whole system, and I don't know what's coming in and out of the domain where I would like to be able to simulate the flow. You can have complicated surfaces. I could have a control strategy where I'd like to change things about the control strategy, and that can really have a combinatorial effect on the amount of simulations I need to do, which just makes it impractical. As soon as I have multiple phases or additional physics, like a chemical reaction, the problem becomes really challenging. And even the notion of a scale resolving and a fully resolving simulation of a turbulent combustion process is, I would say, not currently possible to the full extent. And then in many cases, we're dealing with really extreme conditions. So if I've got a friction Reynolds number well in excess of 10,000, you're really outside the scope of what we can do numerically. But nature gives us the right answer. And so we can use experimental techniques to observe how flows really work. And that can be essential in not only providing us with understanding of fluid dynamics, but also for specifying models that we can rely on in a design process. And so specifically, we're going to be interested in measuring the velocity field. And this is a classic schematic from Scarano that shows different particle-based techniques in terms of the number of spatial coordinates you get, the velocity components you get, and the time resolution. And so it's worth thinking about where we need to be in this box to do a good experiment. So what do we want to be able to measure, ideally? Well, I'd say that we want to get all three components of velocity. That's kind of a starting point. And really, we would like gradients in all three directions. And so we'd like to be able to extract vorticity, and vorticity fluctuations are going to play an important role in the transfer of energy from large scales to small scales. And we would like to be able to observe those dynamics. So we need to resolve a large dynamic range. We have to see large structures, and we have to watch them break down into smaller structures. So we might need a dynamic range on the order of 10 to the 3. And we want to be able to accurately record fluctuating quantities, not just flow derivatives within the field, but also fluctuating quantities on bodies, such as pressure and viscous forces. And that's the kind of library of results that we want to have at our disposal, ideally, in order to really study the fundamental dynamics of a turbulent process. And so that's going to restrict us to tomographic PIV and Lagrangian particle tracking. And for reasons I could discuss in the Q&A, I will basically ignore tomo PIV because it has resolution limits that make it less practical if you really want to do cutting edge measurements. And so we're going to go after Lagrangian particle tracking. And I know this is going to be a computational talk, but it's really important to understand the experiment to see how we're going to deal with the data. So essentially, you have a flow, and you either put particles in that flow, or you have particles naturally, such as a snowflake or a bubble, or a droplet in a spray. And so you're going to shine a light on the flow, and you're going to take pictures of it from multiple perspectives. The pictures kind of look like this. You might have only one camera in some cases, and those are specialized experiments. You'll then try to locate each individual particle in 3D space, and you track it over time. And once you've done the tracking step, you get this scattered set of trajectories or tracks. They look like this. And that can already give you a lot of information, especially about Lagrangian coherent structures and statistics within the domain. But what we ultimately want to do, which can improve the accuracy of both of those things I just mentioned and open up new pathways of analysis, is to reconstruct the full Eulerian flow states. So that's what we're going to be after in this talk, is how do we do a good job of taking the data we get from LPT and reconstructing continuous flow states. So we're going to do that with PINNs, and we're going to use PINNs in a nice way that's going to allow us to really push the bounds of what we can do with them, both in terms of incorporating new physics, in terms of dealing with noisy data, and in terms of representing highly turbulent flows. And so the architecture looks like this. I'll walk you through it. It's modular, it changes depending on what type of flow you're looking at, but it's basically a fairly straightforward application of PINNs to LPT problems. So some of the challenge is going to come in how we deal with loss terms and so forth. But to start off with, in my group, we usually use Fourier encodings. So we've seen nice recent results using Kolmogorov-Arnold networks, and we're interested in using the tweak where you have a spectral basis as opposed to the B-spline basis, which maybe can replace the conventional MLP and encoding combination. But we find that just including an encoding gives you a very robust increase in the bandwidth of flow states, the spectral content of flow states that you're trying to reconstruct. So it's a robust tool, and we always add them. We then have a model for the flow, and here I'm drawing this as one network, but the thing to point out about it is that we found through pretty extensive testing that if you have flow variables with different spectral content, you're going to get more bang for your buck per parameter by having a dedicated MLP for each set of variables that shares a energy spectrum. So for instance, in homogeneous isotropic turbulence, you have -5/3 scaling for velocity, you have -7/3 scaling for pressure. You get a more efficient representation controlling for the number of parameters if you have a velocity net and a pressure net that are separate. But we represent the flow, and we're going to compute residuals for the Navier-Stokes equations. And sometimes they'll be compressible, sometimes they're incompressible, as shown here. We're also going to need a particle model. And this is something that is almost always looked over in LPT reconstructions that use PINNs. And you can do a good job in some cases without paying attention to the particles, but many cases call for a special treatment. So I'll discuss that at length throughout the talk, sorry. And we're going to need an equation that describes the particle dynamics. In multi-phase cases where you've got a solid structure involved, we're going to need a model of that structure as well. And we have something like a moving wall condition, for instance, that will be additional physics that gets incorporated to try to infer the structure response. And obviously, we could have a comprehensive model of the solid mechanics of that structure. But for the problems that we work on in my group, we actually generally don't know the constitutive model for the structure. So we have to try to infer the physical response of the structure from the fluid and moving wall condition alone. All right, so that's just an overview of how this is going to look, and we'll draw on this architecture throughout the talk to do different kinds of things with LPT data. Ultimately, we use just a Monte Carlo simulation to try to compute volume integrals of all of these residuals and then minimize the losses. So there's three things that are really challenging in LPT experiments that you can deal with very effectively if you use a PINN. And that's something that we've been trying to work on quite extensively in my group. And that's noisy data, inertial particles, which are going to be unavoidable in a lot of cases, and multi-phase interactions where we're trying to learn about a structure and we don't have direct access. So I'll start with the first one, which is the noisy data case. And I'm going to discuss it through an extreme instance of noisy data. And that's digital inline holography. And digital inline holography is a great technique. It can give you really cheap and high resolution measurements of very small scale velocity behavior near a surface. The way it works is that you have a single camera, a single laser. You can actually do it with more lasers. That's how Professor Katz's group does that at Johns Hopkins. But in many cases, you use a single laser and a single camera. You spread your laser beam out into a slab and you image it onto the camera sensor. And if you've got particles in between, light is going to scatter off of the particles and you'll be able to record the interference pattern. So you get a hologram and you've got these particle dots with airy disks around them. And you can numerically refocus that pattern to recover an optical field. And you can try to locate the particle. It's going to be at the waist of all of these optical filaments. And I can discuss this in more detail later, but it's not the focus of my talk here. But so you locate each particle, you track it, and you reconstruct the structures as always. What makes LPT hard is that we've got a depth of focus problem, and we have a single camera. And so we're going to get very noisy estimates of the particle position in one of the dimensions, which is the direction normal to the camera, so the optical axis. We're going to have very large uncertainty. And so the resulting distribution is going to be anisotropic, which means that if you just have a default treatment of the particle positions, you can end up with big problems, as you will see. So at the beginning, we're just going to have an implicit particle model, meaning that our assumption is the particle is a faithful tracer that follows the flow, and we can just deal with outputs of the flow model to determine what happens to particles. So we don't have any special model for the particle. What most people do when they reconstruct Lagrangian particle tracking data is they say, okay, I've got the particle at position 1 and position 2. I'm just going to do delta x over delta t. That's my velocity, and I'll assign it to the midpoint. And then I just take the outputs of my PINN. So I query the PINN at that midpoint, and I compare the velocities, and that's what I use to train it. That's the data loss in my network. And that's okay in many cases, but as soon as you want to go to high-speed flows, you start to encounter problems with that assumption that you've got a uniform velocity from time 1 to time 2. And we're going to have bigger issues if we want to deal with anisotropic distribution of particle position errors. So the first thing we said is, well, you could just integrate the particle position. So I've tracked the particle at time 1. I've tracked it at time 2. If I take my PINN solution and I integrate it between the times, I will get another position at time 2, and my data loss can just be the difference between those. But you have to have quite large interframe spacing, and the frame rate has to be relatively low in order for this to be very helpful. Where the technique becomes helpful is when you consider the distribution of uncertainty. So what we do is we have a localization PDF for the particle, and we can advect that entire PDF. So you can do that in a variety of ways. You can do advection of an arbitrary PDF through Monte Carlo sampling. You can fit Gaussian PDFs and advect that, and you can do that very cheaply with a fluid element where you just take principal directions of your multivariate Gaussian, advect the principal axis coordinates, and then fit a PDF, fit a Gaussian to the the sheared and rotated PDF. But in any case, you get a advected PDF, and that would be convolved with the measurement PDF for the sensor. And that gives you a likelihood function, which says, okay, based on my current estimate of the velocity field from the pin, how likely is it that I should have seen the particle sequence that I see for this track? And so we have these different approximations, which are from very expensive at the Monte Carlo technique to very cheap with fluid element technique, but also decreasing in accuracy.
Hi, Samuel. Hi, this is Juan. I have a question.
Yes, please.
I didn't. Could you please explain again this part of this PAB? You said
Yeah.
that you have like your bar. You're starting with your X1, X1 hat, and then you use your ping to move to your to the next step. How?
Yes.
So it would be just like asking your neural network to predict X2, or are you using the neural
Sorry,
network
I should have
more
been more
like?
clear about that. So your neural net, you have the flow model. So you've predicted velocity at the point where the particle was located. And if
Yes.
I predict velocity, I can integrate that over time from time one
Oh.
to time two.
Oh, okay, okay. So you're integrating back.
Yes.
Okay, and how are you integrating it?
So we used a second and a fourth order Runge-Kutta method.
So it's explicit integration. So he goes back to X1 from X1.
Oh, okay, 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 okay. I see, I see. Great. So it's somehow similar to the idea of like neural ODs, right? Because they do something like that. They have like they define a model for one state and they move forward using
Yeah,
Runge-Kutta or that time stepping.
in a sense, yes. In that we're integrating the outputs of the network. So in that sense, it's quite similar to a neural ODE, except that we're not trying to discover that dynamical system here. So we're not trying to discover the dynamics. We're trying to discover the flow behavior. So
Oh,
we're learning the velocity. It's very similar though. You're right. There's a strong analogy.
oh, okay, okay, great. So and then you do it many times to,
For
and
each
then that's
particle. We
for
do it
each
for
part.
each particle, and then actually in the stochastic technique, we do it for each particle many times. So we would have a probability density function that tells us what's the distribution of locations that's consistent with my measurement, weighted by likelihood. And then we
Oh,
advect that entire PDF using the estimate of the flow field that the pin is currently giving us. And that gives us an advected PDF. And then we can determine the probability of measuring measuring the second tracked position, so this blue dot, like how consistent is this blue dot with that advected PDF? There's a convolution there that's based on the measurement system, and that gives us a likelihood function that we want to maximize. We
oh,
want to
okay.
find the velocity field that corresponds to the most probable advection PDF.
Oh, okay, okay, great. That's a great idea. Thanks for explaining.
Yeah, thanks for the question. So we did this synthetically and then experimentally. So first we just downloaded some data from the Johns Hopkins turbulence database. So this is homogeneous isotropic turbulence, and we're going to have a 64 cube volume from that data set, and we'll deal with bigger volumes later in the talk. And I won't go through the details of these experiments in each case. People can pipe in with a question if they or ask later if they're interested. But basically, we form the holograms. We do the standard workflow for getting the particle positions and the tracks out of this kind of data. This is just a representative hologram, what it looks like. So you'll see later when you see the experimental. So remember this picture. When you see the experimental hologram, you'll see that this is very nice. So this is quite ideal. And then this is what reconstructions look like. So on the left-hand side, you've got the exact flow states from the DNS. So you've got U, V, W, velocity components, and you've got pressure. In the central column, you see what you would get if you just assume that the velocities in the tracks are correct. And so we do the velocity-based data loss that you would generally do with a pin. And in the right, you've got the SPAV technique. And so if you look at the velocity in the optical axis, you can see that if you just treat that data as faithful, you've got a very large visible error. So it's incredibly significant and striking qualitative error in the conventional method, but we can actually recover the velocity behavior quite well if we account for the statistical distribution of errors associated with the holographic reconstruction process. So that's a nice result. we see the same thing if we look just at the errors. So these are just velocity differences at all of those same positions. So we use a SPAV data loss, and if we're dealing with really noisy data, gets us a nice answer. We worked with Professor Zhirong Hong at the University of Minnesota to reconstruct some of the data sets from his group. And so here again, you can see it's a lot harder to see the particles in this image. This actually is one of the larger scale DIH experiments that's been done to date. And so Professor Hong's group is really excellent at these experiments. I've got a 5 centimeter tall channel with a 1 centimeter cross section. And the tracks look like this. And so I should have made this a little bigger, but if you look at those tracks, it kind of looks like little pieces of fusilli. And that's not because the fluctuations are behaving like that within the flow. It's just errors associated with the DIH reconstruction process. And so we did the reconstruction again using both of these techniques. And in the conventional approach, we get these structures which look like this. So this is isosurfaces of the Q criterion field. And you get these fully connected, the top and bottom walls of the channel are the top and bottom of this domain. So you should not get these fully connected structures which have no orientation with the flow. When we do our reconstruction with SPAV, we get structures which make sense. You know, it's an experiment. We don't have any ground truth data here, but we get these obliquely flow-aligned structures that are attached to the wall, and they kind of resemble the same structures for DNS in a similar regime. You know, we get an estimate that resolves the field down to the wall. And, you know, if you look closely, you get a better fit to the log law region, although we have very little data in the viscous sublayer and buffer layer. And so we're not getting a perfect match to the Spalding fit in those areas. But overall, you know, incorporating the statistics of the measurement can give us a much better result. But SPAV was very expensive. So for each particle, we're doing thousands of samples for each step to get that advected PDF. And so we wanted a way to just get to the maximum likelihood estimate in a single step. And that also unlocked the techniques that we ultimately developed for dealing with inertial particles as well. So what we do now is we introduce an explicit model. So instead of just having a pin, we're going to have a pin and something else, which is going to describe the velocity of the particle. And that velocity doesn't have to equal the velocity of the fluid anymore. I mean, sometimes we will want it to, but not in every case. And so we start off with just a schematic representation of a track, and we're going to use something called the theory of functional connections to ensure that the kinematics of this particle trajectory are respected. So our model is going to look like this. P is the model. We've got some set of parameters, theta, and the K is the index of the particle. And it's going to map a time to the velocity of the particle at that time. And so if we were to integrate that velocity, we should get that the integral from time 1 to time 2 always satisfies the displacement between the tracked positions. And theory of functional connections gives us a way to enforce this as a hard constraint while we retain an unconstrained optimization of a free parameter. So the way that works, and that comes from Professor Moriarty at Texas A&M. And so we've got this is just a single component for simplicity, but we've got a free function G, which can take any form. And we've got a set of constraints that I won't go into them in detail, but these are formulated. We've got a preprint which gives the derivation in a nice sequence, but we're going to have projection coefficients, which are going to ensure that that integral is satisfied, and then switch functions that turn those projection coefficients on and off. And the result is that for any free function, I can come up with these constraints such that the resulting function will always satisfy that advection equation. So I'll skip over some details that aren't super important here, but we can factor that into a matrix form, which is going to be very nice for inputting it into a TensorFlow or PyTorch, or pick your favorite differentiable programming environment. And so we've got a vector of times, so just polynomial increments of t, and we've got some matrices that we can compute ahead of time. The important thing that I want to note is we've got this vector delta, and that describes the displacement between particles. So if I really trust my data, I can just ensure that that is respected as a hard constraint. But if I don't necessarily trust my data, now I can shift these particle positions around and and without changing anything else. And so then I can have a data loss, which says, well, I expect those positions to be close to where I track them, but I will use the PDF that I described earlier, this localization PDF, to discount particle positions that are very far away from the track location. But we've got some flexibility. And then we've got this totally unconstrained parameter theta, and unconstrained is nice because we want to use SGD to optimize these alongside the PINN. And so these are random draws from theta, and you can see that no matter what I say for theta, I will always get a velocity history that integrates to the tracked positions. So this is the explicit model that we're going to use in the optimization. So we've got one of these for each particle. And, like I've been saying here, we can optimize theta and delta, and no matter what, we're always going to satisfy that advection equation. And we can also just fix delta if we've really got highly trustworthy data. So all of that relates to that yellow box from before, the particle model. And so we have a physics equation which says that I expect the velocity of the particle to match the velocity of the flow. And so that will relax later. But for now, we're just going to assume that we do want those velocities to match. But we're going to allow the position of the particles to float. And so here I'll show an example where we've actually got a much lower magnitude of noise. And this is inspired by a more conventional PTV experiment. And it's a much larger box. So this is already getting to be quite a turbulent flow. So it's the level of turbulence is the same, but it's the bandwidth of the function that you have to represent is much broader now. We've got more low frequency content. And so again, we've got some information about the experiment, which I can come back to if people are interested in it. But the takeaway message is the reconstruction serum. And if you look closely, so here again, we've got a snapshot of the DNS. We've got U, V, W, components of velocity and pressure. And all of these reconstructions are quite good. The level of noise here is about a factor of 10 lower than for a digital inline holography experiment. But you can see if you look very closely, and I'll show you errors, that if you inspect these, you do have higher frequency content being resolved as you go from the conventional technique. So just assuming that the velocity that you get from your track, so maybe you've got LaVision software, or maybe you've got your own tracking software, but if you take that velocity as the truth, you're doing a bit of filtering because you've got errors in your data. If you do SPAV, you get a better result than if you do the conventional method. And if you do this neural-implicit particle advection thing, which I've described just now, so this explicit particle model, you're going to do better still. But the key point is also that, or a key point, is that we've reduced the cost by nearly an order of magnitude by shifting from SPAV to NEPA. So now the cost is totally on par with the conventional method. And so simply by adding a particle model, we can deal with the noise more effectively. And if by eye, if you look at errors, you can see, okay, we've got high errors and then we've got smaller and smaller errors. So you're getting a much more faithful reconstruction the further you go. And
I have a question because before you use, I think, the same database and the conventional was not as good. What makes conventional good in this case?
Yes, so I should have, this is just the data sets I had on hand for making slides, unfortunately, but this is much cleaner data. So it's about an order of magnitude less noisy than the DIH.
What do you mean cleaner?
So this is recorded with multiple cameras, and the particle localization step is very accurate.
Oh, so it's experimental data set.
This is still synthetic. So I'll show experimental data in a few slides.
So where is the camera? Why do I need, if it's synthetic, why do I need cameras? You mean the way
we
you
simulated it because this was part of a benchmarking campaign that we did with LaVision and DLR. So we wanted to understand synthetically before we did experimental evaluations how we expected the reconstructions to perform with.
So how do you model the camera?
Sorry?
How do you model the camera? What camera captures?
In this case, so this would correspond to the level of noise that we would see in a multi-camera case, but we're not modeling the cameras here.
How do you introduce the noise?
It's random Gaussian errors with a slightly elongated uncertainty along the.
Okay, that's a better way of saying it.
Okay. Okay, sorry.
Just
I'm used to talking to experimentalists, and so then it's like, oh, sure, representative noise for multi-camera. But yeah, no, it's additive Gaussian noise. We've got a factor of 2 to 1 uncertainty in the Z direction.
Got it. Thank you.
Yep. And so we do see a decrease in error as we go from the conventional to the stochastic PAV, and it's about a 50% and then about a 25% reduction in error, but they're low levels of error. So you're getting most of the low frequency content, and we're just really trying to refine the higher frequency estimate. But so if you look at an individual particle, you've got a distribution of error, which looks like this. So the red dots are the tracked positions. The green line is the true position, and the blue line is the optimized track. So the optimized track is sitting totally on top of the black track. You can kind of see it if you squint and you look at the ends, but the optimization is quite effective. So the algorithm is moving the particle positions around, and it's trying to find a track that's consistent both with the data that you've recorded and also with the flow that's going to satisfy the governing equations. And so you can see that if you look at position, velocity, and acceleration, this is all in the Z component of each of these things. Because that's the noise, that's the direction where we're more noise affected. We have very accurate resultant track estimate after the optimization. Then if we look at statistics for the entire set of tracks, these are probability density functions. So again, here blue is the data. Actually, sorry, this is flipped, which is my fault. But blue is what we started off with, and the red PDF is what we ended up with. So you can see you have lower uncertainty in X and Y and larger uncertainty in Z. And then we have a much, we're able to recover like more accurate positions of the particles. So it's not necessarily something we care about, but it's an interesting thing to note about the algorithm is that we've pinpointed the particle locations much more effectively when we combine that localization step with the flow reconstruction problem. So we did extensive benchmarking, and that's where this notion of the camera came about and why we wanted to understand how this worked with the much lower levels of noise. We did an extensive benchmarking campaign with LaVision and with the DLR. And the reason for that is that those groups have produced the Vic-Sharp algorithm within the LaVision Davis toolbox, which is probably the predominant commercial tool that's used for Lagrangian particle trajectory or tracking, sorry. And the DLR has a flow fit algorithm, and between the two of those are sort of the state of the art in what people do for data simulation for LPT in general. I think both of those groups are probably interested in experimenting with PINNs now, but these are sort of the legacy algorithms that they've developed over the last decade or so. So we wanted to see how the PINNs compared. We did, so there were a lot of synthetic tests. I can send a conference paper which details those for anyone who's interested. But we also did a turbulent boundary layer that was measured at the DLR in Göttingen at the 1 mg tunnel. And so this had a friction Reynolds number of approximately 1,000, and they were able to track 54,000 particles, which is quite a lot. And what we did, so I'll show nice reconstruction results, but first I'll just show you the results of this, which be a boon to people who like PINNs or enjoyable to folks who like PINNs. But so what we did to benchmark the accuracy of the algorithms is we kept 20% of the tracks as test data, and the algorithms were cloaked to those tracks, and we used 80% of the tracks for reconstructions. And we did reconstructions first with all of those 80% of the tracks, and then we cut the 80% in half, and then we cut it in half again, and then we cut it in half again. And so we went from on the order of 50,000 particles to on the order of 4,000 particles. And here you see the accuracy as benchmarked by those 20% of tracks which were withheld from the reconstruction. And so this green line here is PINNs, and you can see that we do very well using PINNs. From the highest seeding case, we have a very excellent reconstruction, and even as we fade out, we're achieving reconstruction accuracies that are kind of comparable to how the other algorithms were performing with 8 times more data. So these are isosurfaces of the Q criterion field using the different methods, as well as a binning method which performs quite poorly. But you can see that if you look at the structures here, you've got a lot of corruption due to noise in the flow fit from the DLR and in the Vic-Sharp from LaVision. And so it's a challenging flow case to reconstruct, and the algorithms work very well across a large range of flows. But once we go to this kind of condition, we're at an operating condition where, the pins are able to provide a large benefit in terms of reconstructing flow derivatives with a high degree of accuracy.
Can you say something about Vic? Because it's totally wrong. I mean, it seems that it
Yeah.
spread fictitious structures, fictitious tricks, which are not there.
So there's a couple things to say about it. I mean, just trying to think of the order in which they use a sequence of steps in the reconstruction where they start off. They've assumed inviscid flow, and so because this is very near wall, I think that that's probably a contributing factor to what you're seeing, the amplification of noise in the field there. And what they do is I'm trying to think of a good way to explain it. So they've got they estimate the vorticity field, and then they can estimate the material derivative of vorticity, and then they use the vorticity transport equation, and they solve a sequence of Poisson equations to get from vorticity to velocity to pressure. And then those fields get included in an optimization. I mean, I haven't worked on the inside there. I'm not sure about the details about how that algorithm works, except for that level of description. But the other thing that I should just say that's sort of a little bit exculpatory here is that, these are flow derivatives. So if you look at the velocity field, the large scale structures are pretty accurate across the board. But the high scale features are relying on this like very multi-step process that they're going through to reconstruct the field, which involves, they parameterize everything in terms of vorticity, they solve multiple Poisson equations, and the instantiation of the vorticity transport equation assumes viscosity 0. And so my assumption is that that is probably one of the limiting factors in the reconstruction.
Okay, thank you.
And then we looked at pressure as well. And so this is going from the full reconstruction with all the particles to the reconstruction where we have the fewest particles. We said, well, let's assume that pressure is pretty good in the case where we've used all the particles. And this kind of gives you a sense of that qualitatively. So even though we had those problems with the Q criterion field from Vic Sharp, the pressure structures aren't bad. They look pretty good qualitatively, even in this case with only about 4,000 particles. But there's an issue in Vic Sharp that we don't totally understand where it comes from, where you've kind of added a large-scale pressure gradient. But the PINN-based technique and the DLR method, they actually perform reasonably well on pressure, even when we've downsampled the data a lot. An interesting thing to note is just the ability to grasp the real solution as you fade out the number of particles. So this plot here is showing on the y-axis the normalized error content, spectral errors. So we've got errors. It's the spectrum of the errors for the reconstruction normalized by the amount of energy of the flow at that wave number, and the x-axis is just wave number, and the color of the lines indicates the particle spacing. So as we go from the bright yellow line, we've got particles that are very far apart. And as we go to the blue line, the particles are very close together. So this is from that homogeneous isotropic turbulence case, and these are Kolmogorov separations. These vertical lines here show the Nyquist frequency based on the particle spacing. And so you can see the Nyquist frequency obviously is going to go, down as the number of particles is reduced. And the way to look at this, and sorry, so the solid line is pinned. The dashed line is what you get by interpolation. So this algorithm was introduced by Jimenez in the 90s when people first started thinking about particle tracking. And, there's an early JFM paper by Jimenez where they kind of did the modeling of what you expect to reconstruct in between the particles. And the conclusion was essentially, well, you shouldn't get anything. And that's what we see with interpolation-based methods here. If this plot is, these are the same plot, but now I'm switching from absolute wave numbers to wave numbers relative to the Nyquist frequency. And so what you see is the interpolation methods asymptote to 100% error at the Nyquist frequency, which is exactly what you'd expect. If you're just doing interpolation, you don't get any good information in between the particles. Conversely, the PINN, even at the sparsest case, so here you can imagine in a box of isotropic turbulence, it's like we've got 8 particles in a box that's 24 by 24 by 24 Kolmogorov length scales. We're still getting a reduction of error up over an order of magnitude by using a PINN to reconstruct it. So that suggests that you're grasping some fundamental dynamics of the flow, which give you resolution beyond the sampling resolution of the particles. And then that error decreases exponentially as that cube shrinks. So as you're able to add more particles, you get you get an exponential convergence to the full resolution of the flow, getting all the spectral content. And so this is, I think, very convincing. So some people have asked whether PINNs are simply interpolating, and I think this is very strong evidence that they don't interpolate. They're actually grasping onto the solution even at wave numbers that are higher than what you would resolve with the particle positions alone. So I think the most interesting part of what Ko has done in this work is his work on inertial particles. And this becomes really important in a lot of LPT experiments. And this is where it's so cases with noise, there's various ways of dealing with it. Once you get to inertial particles, you have to consider additional physics, and there's not really another option. So this is an animation of a stagnation flow, just to give you a sense of what I'm talking about. There's streamlines in gray, streak lines in gray, and we've got particles that are colored by their Stokes number. So these would be bigger or smaller particles, or heavier or lighter. And the very bright particles have a high Stokes number. The very dark particles have a low Stokes number. And if you look closely, you can see that the dark particles kind of follow the streamlines much better than the light particles. And so for Lagrangian particle tracking experiments, we're going to be dealing with particles that are quite small relative to the Kolmogorov or viscous length scales of the flows that we're looking at. And so we can use the Maxey-Riley equation to model the particles. And so we're going to write it out in this form here. Because I'll talk about error experiments, I'm going to ignore everything in orange. So I'm going to look at viscous drag and buoyancy effects. But if we were dealing with a liquid phase experiment, we would have to consider the full equation, which it's not challenging to do. The PINNs make it actually quite easy to handle the full equations. But for what you'll see, we're only going to have these 2 blue terms. And in the first case, we'll be able to assume that we've got creeping flow. So we've got a particle Reynolds number that's much less than 1. And so then we can produce this simple expression for the relaxation time, which is basically a characteristic time scale that will say if I impose a step change of velocity for the flow surrounding a particle, what's the exponential convergence rate for the particle to catch up to the flow speed? And so that's going to be a function of the fluid density and viscosity, but also the particle density and the particle diameter. And that's going to be important. Okay, so again, why do we care about this? Well, if we think about some real experiments, this is some beautiful data taken by a good friend of mine, Vedant Nair at Georgia Tech. And this is jet and crossflow particle image velocimetry. And here you see these beautiful dots. And you see a jet, and you see this nice vortex roll up at the outer shear layer. And what you'll notice is that you've got these black cores, and those are the cores of the vortices, and they're totally void of particles. And Vedant was using titanium dioxide particles in this experiment, which are very small. They're in the order of 100 nanometers. But the particles tend to cluster together due to intermolecular forces, and they can be more on the order of 1 micron to 10 microns by the time they reach the measurement domain. And at that point, they will have an appreciable Stokes number. And so if you look at this kind of data, and if you take these tracks, and if you say that you're going to assume that velocity is the flow velocity, you will get the wrong answer, because those particles become inertial by the time they come into your domain. And if you see features like this, vortex cores void of bubbles, you have to somehow extend your treatment of the data to account for the particle dynamics. You see very similar thing in a lot of rotorcraft experiments. So these are bubbles in this case, helium-filled soap bubbles. And this experiment was done by LaVision and DLR. And again, they've got these vortex cores that are void of bubbles. So you know that the bubbles are kind of getting spun out of those cores. Another big area that we're interested in is dealing with shocked flows, and particles are going to struggle to keep up with the flow when you go through a shock, or actually, as you go through the shock, the particles kind of punch through and they they travel ballistically, and then in the expansion fan, they're going to lag the flow as it speeds up much more quickly than the particle is able to, and that results in blurring out shock waves and moving them into the wrong position. And there's also many experiments with natural tracers. So these are snowflake measurements by Zhurong Hong at the University of Minnesota and bubble measurements by Professor Ray Nee at Johns Hopkins University. And both of those flows are subject to either significant gravitational settling or buoyancy effects. And bubbles can also have surfactants. You've got issues with geometry when you're dealing with snowflakes. And so for many experiments where people are tracking particles, they're going to deal with the transport of the particle not matching the flow properties at that location, and then we want to be able to accommodate that data with our PINN. So I'll go through two cases. In the first case, these are both synthetic. We're working on experiments to deal with these at the moment, but we have not done this experimentally yet, but we've got very strong evidence that suggests that we can deal with this kind of data. So this is a bidispersed case, and we're going to revisit that same homogeneous isotropic turbulent flow. And so we've got two sets of particles. We've got a small set of particles, and they're colored by their diameter in these plots. And those particles are about on the order of 20 microns. We've dimensionalized the flow to be air. And the large particles are about 70 microns. And you can see that these small guys are kind of swept around isotropically. But they have a Stokes number on the order of about 1, so they're about 100 times higher Stokes number than what you would want for a PIV experiment. The large particles have a Stokes number more on the order of 5, and there you can already see that you kind of get this aggregate settling behavior. And the data that we get is that we have all of these mixed up together, and we do not know anything about the particle diameter. So what that means is that we're solving Navier-Stokes equations with the PINN, but we also have to be able to solve a Maxey-Riley equation for each particle with a parameterized diameter. So we don't know the diameter of any of the particles a priori. Again, we've got the same exact flow state to the left. If we were to reconstruct this using the best method we have, so we use the method that I showed you earlier where we're trying to change the particle positions and so forth and trying to get an accurate reconstruction, except that we don't model any of the particle dynamics. So we say the particle's a tracer. So flow velocity equals particle velocity. We get results that are qualitatively okay in the X and Y directions, but in the Z direction, you can tell that we've been totally thrown off by the settling behavior. And if we don't get all three components of velocity, we cannot reconstruct the pressure. When we do the full model, where we're trying to recover not only the flow states, but also determine the properties of each individual particle and solve the Maxey-Riley equation for each particle, we get a good reconstruction, and this becomes especially pronounced if we look at the errors. So even when we thought we had qualitative agreement, we actually had quite large quantitative disagreement. And that's because even those small particles were not tracers. They were not faithful tracers. They had large Stokes numbers, and they gave us the wrong velocities. Whereas with the inertial reconstruction, we get everything quite well. So you get nothing really in terms of flow derivatives with that model where we assume faithful tracer behavior. When we assume that we've got inertial particle dynamics and we try to get everything out of it, then we can get good estimates of the flow structures. We don't get absolutely everything, but we get a lot of the derivative content correct. And what's really striking is if we look at a joint probability density function of the particle diameters that we've estimated. So on the y-axis here, we've got our estimate for the particle diameter, and on the x-axis, we've got the real diameter. You can see that at the beginning, we initialized with a distribution that was totally incorrect. So there's no mutual information between the predicted particle diameter and the estimate, and the true value at the outset. But then once we trained the network and did that reconstruction, so this is together with the flow reconstruction optimization, we've managed to get the size of each particle with a very high degree of accuracy. And so not only did we classify them correctly as small or large, we actually get the size right within those distributions. What we're really interested in is doing this for supersonic flows, because that's where these inertial effects become totally unavoidable. So we came up with an experiment, or we came up with a set of a physical regime where we expect to be in a supersonic wind tunnel. So we'll be testing this next year with AFRL. but we don't have experimental tests at the moment. And for now, what we've done is we've done a steady case. So time resolved cases are being performed now, but the first thing we did is we just did this with a steady reconstruction. So this is an axisymmetric cone cylinder shock structure. So we've got the shock attached to the nose of the cone, and we've got an expansion fan in the wake. And the number of particles and interframe time that corresponds to what we could actually do experimentally. So this is a flow speed plot, but you're also seeing the particle speed. So if you look, you've got all these, it looks like streaks that are going through the shock and then in the expansion fan here. And that's when the velocity of the particle does not match the velocity of the flow. So upstream of the shock, the particles are in equilibrium with the flow, and you don't see any streaks. Within the shock, you see a lot of streaks because there's a big difference. There's a large slip velocity. A point I could make in a more extended way later is that a lot of people kind of treat particles in PIV experiments as if they have a constant relaxation time, but that's not actually sufficient because when the particle passes through the shock, as the compression and rarefaction effects, they're very sensitive to the local conditions. And so you're going to get a response time of the particle that can change by up to 50%. And so you actually, this is just a probability density function of the change of the relative response time, the change in response time of a single particle track. So that just says that you have to have the full particle dynamics. You can't just assume that you've got a static response time in a supersonic experiment. So here's the real velocity, or the ground truth velocity, density, and pressure fields. And if we do the reconstruction where we assume we have tracers, we get results that are a little bit too blurry and the shock is in the wrong location. But what I should say about this is that pins are really letting us do something here that you couldn't do without a pin, or people have not done without a pin yet, which is to say that there are no, to my knowledge, there are no LPT data assimilation algorithms that reconstruct velocity, density, and pressure from particle tracks for a compressible flow. And this was actually relatively trivial. You know, we don't need to do any sort of fancy numerics to handle the compressible Navier-Stokes equations. We compute an average inflow condition based on the stagnation conditions, and using that, your pin can grasp the solution very effectively. And then we can do better still if we include the dynamics of the particles. And so again, we don't know the size of any of those particles, and we've got a random distribution associated with the amount of agglomeration that you get, which varies from particle to particle. And in reality, we'd also have a different density, but we didn't account for that effect here. And so we do the reconstruction where we're solving Maxey-Riley equations, and we're solving the compressible Navier-Stokes equations for that set of particle tracks. And what I should say here is that the drag model now becomes more of it becomes something that you have to worry about. And in this case, I didn't present the equations in the slides here, but we use the full Loth drag model. So we're calculating based on our current estimate at any given instance for the pin, and for the particle model, we calculate the particle Mach and Reynolds numbers, and then we compute drag using the Loth model, and we then use that effective value in the Maxey-Riley equation. So we get an excellent result when we bundle all of those things together, and you can see that in the errors as well. So you put the shock in the right point, you get a very crisp shock structure. And again, we don't have to do all sorts of fancy numerics to get this to work for a compressible flow. It's relatively turnkey. We just need to have the right models to interpret the kind of data that we have. And again, we initialize the particles. This time we had a slightly better initialization than before. And there is a multiplicity of solutions that we're dealing with, so we don't get the same level of accuracy for these particles that we did with the previous particles, but we can size the particles well enough to be able to do an accurate reconstruction. So we've got very low errors in the velocity field here. See how I'm doing for time. Okay, I will kind of not spend a lot of time on the multi-phase part, but in essence, I mean, you need to introduce a model to deal with a moving solid. And so we've got problems. They're actually mostly not involving PIV. They would involve 4D flow MRI, so a magnetic resonance imaging technique. but we're using PIV just to make the point of how you incorporate a structure into your reconstruction here. And many of the solids that we care about, like I said, we don't have a constitutive model, so we're restricting ourselves to modeling the physics of the flow and the physics of that boundary condition. So there's just two synthetic cases. We've got a flexible beam, and we've got a compliant pipe, and so we're going to send an impulsive pressure wave through that pipe. The beam is attached to a bluff body, so you're going to get a von Karman vortex street in the wake of the bluff body, and it's going to kind of talk to the surface there, and then you'll get this flexible behavior. And so ultimately, we would like an arbitrary parameterization of the surface. But what we did as a first pass is we said, well, we'll have some modes available to us to represent the surface states. And that could either be through bending modes, which is what we did for the beam. So if you do have a reasonable constitutive model, you can just compute bending modes a priori. And for the pipe surface, we cheated. We just used data-driven modes. So we did a pod decomposition of deflections of the surface. But if I have either set of modes available to me, I can represent the surface as a mean surface position plus the modes times a set of coefficients. And we just have another network which describes those coefficients. And then we apply a moving wall boundary across the surface. And that's all that we need to do to incorporate this extra set of physics into the problem. So again, you've got these flexible modes. We didn't want to regularize with the number of modes, so we incorporated way more modes than we need. I'm just showing 2, but we used up to 8 or 10 respectively in these problems. And we're not sensitive to the inclusion of more or fewer modes. And these just show the modes that are responsible for most of the energy content of these surface fluctuations. We then simulated particle data for each case. So here you're seeing what the particle trajectories look like and what the images look like for the flexible plate case, the flapping plate, I should say. And you'll notice that you can see a number of particles that have made their way into the recirculation zone. But actually, if you look at the tracks in that area, you have very little information close to the surface. And so we're going to be interested in how well we can reconstruct the dynamics of that structure from data that becomes increasingly sparse as you get close to the structure, where hopefully the PINN can use flow physics and that boundary condition to fill in the gaps. And so this is a reconstruction of vorticity and pressure. So here you've got the exact fields on the left, and you've got the reconstructed fields on the right, and you've got errors. And so these errors are very low. So we're all single-digit percentage point throughout the field. And the modal response is correct for those leading modes. It's good for everything, but the energy decays quite fast. You'll notice that you're not totally getting the behavior at the tip. And that's, like I said, you've got a very sparse information at that location and really along the entire pipe. But for the most part, you're getting the dynamics of that well. And to absolutely nail what's going on at the tip of the plate, you would need a much more precise solver. So, we're playing around with different ways to really drive the residuals to machine epsilon. But at the moment, the model with if you give it full field information, you can drive the residuals to tolerably low level, and you can really nail the structure response. But if we're just training on sparse data for the fluid, then we have this problem. And so it's possible that it's an information limit, but I think probably it's a limit with the precision to which the residuals have been minimized. We did the same thing for the impulsive pressure wave. So here the data is much more subtle. I mean, you can kind of see that wave traveling through the particles, but it's very minimal. You can see it a little bit in the tracks. And it's the same story as before. If we look at the UVW components of velocity and pressure, we've got exact fields, we've got reconstructed fields, we get very good results. We get very low quantitative errors. And we reconstruct the dynamics of that structure with a high degree of accuracy. And so that kind of gives you a pathway for how to deal with FSI. And so to do this, it's a relatively challenging inverse problem if you've got sparse measurements of a single phase and you want to reconstruct a multi-phase process. But PINNs are very robust to inclusion of multi-fidelity, multimodal data, and we think that it's really the right tool to deal with that kind of a problem. And so in terms of wrapping up what I've discussed with you today, one thing to think about is what gives rise to the measurement you're looking at. So thinking about the distribution of noise, the fact that velocity might not actually be constant between frames, those become very important, and the fact that your particle positions might be in the wrong place. That's incredibly important to consider if you're processing real data, especially if you're trying to reconstruct high frequency energy content in a highly turbulent flow. The Lagrangian particle tracking data is really rich. So despite the fact that we have in some cases very sparse particle fields, we can still get accurate velocity information in between the particles. So the PINN is not just interpolating information. I think it's nice to confirm that what the PINN is doing is it's actually grasping the dynamics of the flow at energy scales that are at higher wave numbers than the particle spacing, the particle Nyquist frequency. And lastly, there's plenty of ongoing work to be done. So one of the things we're always interested in is how do we increase the expressivity of the network. And so multi-GPU models, for instance, or dealing with maybe a Kolmogorov-Arnold network using a spectral parameterization of the edge functions, or as the Crunch group is now doing. I think there's many different ideas out there on how to do this, but this is kind of a pressing and ongoing research need, is how do you make these represent more turbulent flows over larger domains for longer time horizons. And we're also interested in understanding the scaling of reconstruction accuracy with the particle density, sort of normalized with respect to turbulent scales. And lastly, when it comes to fluid structure interactions, we'd like to be able to take what we did as an initial effort there and make it much more arbitrary to the surface. So using either neural level sets or something along those lines, we want to be able to deal with a surface where we don't need kind of an a priori modal analysis of the surface or a constitutive model to get the representation of the structure embedded in the reconstruction. But that's my talk, so I really appreciate your attention, and I'm happy to take any questions.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any questions from the audience for the speaker?
So, Sam, thank you very much for the talk. I have questions. I will ask them later, but I just want to tell you that you didn't come only to the home of PINNs, but also to the home of Martin Maxey. So Martin Maxey is attending the talk, and maybe we can invite him first to see if he has any comments or any questions.
All right. Good to see you. And I enjoyed the talk. It was a lot of ground you covered. I was impressed the fact that you could do the particle sizing, because in so many experiments, you have an idea of what the particles are, but you don't really know for sure. There's a spread in that. Mm-hmm. Being able to incorporate that is really significant. As far as the particle tracking equation goes, when you've got the gas-solid problem, you're on pretty good ground. When you do the liquid-solid case, this history term kicks in, and people argue all over the place about it. And it really is just a low Reynolds number correction. And sometimes do you have an infinite limit to the integral or not? In practice, it's probably better to truncate it at some empirical level, and you probably get a better match to the final answers. Mm-hmm. But overall, and we didn't get to really hear about the snowflakes, but I can see in a meteorological context, if you're able to do anything with ice crystals or snowflakes and so on, there's a sort of plenty of scope for loading atmospheric data later on.
Absolutely. So Professor Hong is the one who does those experiments, and he uses these floodlights. He's in Minnesota, so he has to get something for dealing with all that cold weather. And what they do is he uses floodlights, and they illuminate a giant column of air over quite a few meters, so order of tens of meters. And then they've got quadcopters that fly around, these drones, and they've got cameras embedded on them. And they are able to kind of self-calibrate and track snowflakes over a very large column of the atmospheric boundary layer. And so that's sort of the experiment that we had in mind when we first started doing this. And then we realized that's going to be really hard. So
Yeah.
the dynamics of the snowflakes are the parameter space is a little bit too large for us to deal with at the moment. So we're focused on supersonic flows. But yeah, the atmospheric boundary layer case is really interesting, and that's where we would like to take this ultimately, and in working with Professor Hong. But thank you very much for, I mean, it's an honor to present to both you and George here.
Yeah, no, great talk. Thank you.
Thank you.
Do we have any other questions or comments?
Juan, you have questions? Or maybe Savas? So there's a couple of people who are doing imaging work. Yeah.
Yeah, yeah, I have a
Introduce-
question.
Can you
Savas,
introduce yourself first?
Yeah.
Yeah,
Can
sure.
you first introduce yourself? Yes.
Okay. Hey, I'm Siavash. I'm doing a postdoc with George. I joined here a few months ago. Yeah, so very nice talk. A lot of interesting results. So my first question is that in the supersonic example that you showed, the shock one, I'm assuming you use the residual loss from the equations, also the data loss, right?
No.
So you didn't use data loss?
So those were synthetic cases. So the particle positions were assumed to be accurate, and we used the KCT formulation there, so the kinematics constrained tracks. So the particle positions were embedded as a hard constraint, but the velocity history of the particles was optimized. And so the way that the data comes in is that the positions are fixed, but we don't know the velocity between them. And that velocity gets optimized such that between the flow velocity and the particle velocity, you solve both Navier-Stokes and Maxey-Riley.
Okay.
So Savas is not because Professor Moratti gave a talk here, but I don't think Savas was a. So we had a postdoc who was working on the theory of functional connections. So it's basically hardwiring the constraint, Savas. Okay, it's
Okay.
like the lifting method in Galerkin method, for example, if you have non-zero Dirichlet boundary condition, something like that, or varying boundary condition. So it in some sense it is satisfied, but automatically, but not in the data loss. Not with the penalty constraint, yeah.
Okay, I got it. And then can you go to slide 28?
Yes. This one?
Yes, yes. Can you show these results, the conventional one and the SPAV one? Yeah, so this, if you look into the W component, so it seems to me that the SPAV is actually smoothing a bit, right? So I'm guessing this is the noisy data, but if you go to the future slides where you have less noisy, SPAV it's much better.
Yeah. Yeah.
So over there, it seems that the high frequency is being lost in the conventional method, but here to me, it looks like it's being lost in the SPAV method.
Well, the conventional method doesn't get anything.
Yes, that's it's giving the wrong answer, but the SPAV is also, it seems it's smoothing, right?
You're right. So, but if you look at the U and V components, I wouldn't say SPAV. Well, you're right, actually. No, it does look a little bit more. It looks filtered, but actually, the high frequency content in the conventional estimate here is spurious. It's not actually accurate. And so, and then I drew attention to this for obvious reasons. But if you look at the errors, each component of error is higher for the conventional data loss than the SPAV data loss. So I wouldn't say it looks like a lower frequency estimate, and in some sense, the spectral you have larger high frequency errors in the conventional. Sorry, what I should have said that differently. I should say that the error content of the conventional at high wave numbers is significant, and you're kind of by eye just attributing that to the flow, but it's not correct. I mean, this looks smoother, but it's reconstructing the flow more accurately. Not sure if I'm saying that.
I get, yeah, I get that. And then one final question. Initially, you said that you have one encoding that you take it to basically Fourier domain. Is it right?
Yeah, we use
the
a
very
Fourier
first
encoding.
slide.
So,
so
right,
that
it's
encoding
essentially a random Fourier basis. So you've got sine cosine pairs, and you have maybe 100 to 250 of these things.
So I'm just wondering if you tested also what happens if you just use MLP over there.
Oh, then you get huge implicit regularization by the network. You lose most of the high frequency content.
Okay, so it's right there.
Yeah, yeah.
So
Okay.
Shabas, this is to deal with the this is standard technique to deal with the multi-scale features,
Okay.
high frequencies. That's so the spectral bias, basically. So Paris and Wei Chai and other people have introduced it a long time ago.
Got it. Thank you.
But I know that there was recent work using cans from the Crunch group, and that should maybe have the same effect as using an encoding, or maybe even enable better reconstruction. So that's something we haven't tried yet.
Yeah, cans suffer less from the spectral bias, but eventually it depends on how the representation. But yes, different representations would give you that. But it's like think of this as a feature expansion. Yeah, or basis enrichment. It's called in finite elements. Any other questions before I ask my questions? Okay.
Maybe I can ask.
Yeah, you can ask. Yeah.
Okay. First of all, thank you so much, Samuel. It was a really nice talk. Thank you so much for accepting the invitation. Also, I have a question here. First, for example, your Fourier features.
Mhm.
I have played with them a little bit, and I agree that they work quite well. But
Yep.
usually they struggle when you have some type of noisy data. Because when you have noisy data, you will have some high frequencies that should not be there, but the model will try to get them for some reason. And then if you train them, if you don't train them carefully enough, then your results end up to being a bit messed up. So have you done something else when you deal with noisy data? How do you use the Fourier features? So do you have any?
Yeah, so we haven't found that to be an issue, but that's because we're formulating our data loss in such a way that we try to discount, like if you have noisy data, I can't say that I've tested that extensively, so I don't know. We haven't really encountered an issue with it. So we have cases, I mean, if you're using the governing equations for the flow, and you've got an appropriate data loss that discounts the data based on the level of noise that you anticipate. If anything, usually we have a flow that looks like you saw with SPAV to have lower to be blurred or something like that, which is just because you don't have enough information from the data. So we kind of have the opposite problem. As we increase the magnitude of noise, we lose what apparent detail in the flow, whether it's true or not, because we're discounting the data much more heavily. So we always instead of using a 2 norm, we always kind of have a 2 norm that's weighted by the uncertainty of the data. So we would have just an L matrix in there where we take the Cholesky decomposition of the noise covariance matrix, and then we do an L norm data loss. And so I couldn't speak to the details of why that would never be an issue, but it's not something we've encountered with these types of data, but we'd be happy to look at cases.
Oh, okay. No, actually, when you're just trying to reconstruct things, usually that doesn't. It's okay because you have data that kind of balance things out, but usually you face them when you're trying to infer hidden fields. Like for example, as we did in the paper, right? You have velocity, so you have to know what's happening with the temperature. That also I have tried them, and for example, if you change the encodings for it with Chebyshev, you don't make them trainable. You just instead of using the Fourier mode, you use like Chebyshev polynomials. That usually helps for that. Also, and I have another question regarding like the particle model that you're using. First, do you train that? Because there you have also some trainable parameters, right? If I understood correctly.
Yes.
Do you train that beforehand, or do you train them all at the same time, like in parallel with your physical
Yeah.
also in your?
It's one optimization.
Oh, okay.
Yeah.
Yeah, I see. Because actually, we that was essentially to deal with the noise, right? And of the data, right? And actually we do
Both noise and inertial effects.
okay. Yeah, actually we do something similar. Maybe it was like in one paper that was published about it. It was like reconstructing some flow in the MRI. And the thing that we do there is like we have like two networks, like one network predicts you the mean fields and the second network will predict the noise.
Sure.
And then we're going to assume that the mean field what we're observing is what is going to follow the equation, but not the noise. And we
Okay.
assume that this noise comes from a normal Gaussian distribution. And for example, for linear problems, because we were lucky, the Reynolds number was small, so we could use the Stokes flow. You can use something like the negative log likelihood, and then you get a model. And then, but what I'm bringing this up is because in our case, when you would try to learn both things at the same time, the optimization became, I mean, if you train for long enough and you wait long enough, you will get there. That's not a problem, but it will take much, much more longer.
Mhm.
And that comes for a question because when I was watching, like, your model is quite interesting, and but it looks like, for example, you're also using like your hard constraints, right? You said that you're using the hard constraints from you say the TFC.
Mhm.
Yeah. For example, in my models, I usually also use something like, let's call ADF, and it's similar it's a similar idea. And also, for example, I usually try to enforce some kind of divergence-free fields,
Mhm.
which is it's just playing with automatic differentiation. Is kind of, but what I'm trying to bring with all of this is like, every time that you add a hard constraint, it's true, your solutions will match the data or what you wanted to do more closely, but the optimization problem becomes harder.
Yes.
And then was like other question, like for example, when you do all these things like with the SAB that you're in the beginning, you're trying to trust the ping to get the distribution, like you to get like all these multiple points and you get the distribution. Do you do it
Mhm.
from the beginning? Because most likely, since your optimization problem is so hard, at the beginning of the training, most likely the ping is going to give you things that may not be so accurate. So they may be pushing you away from the true solution at the beginning of training. So it will
Mhm.
make the training process a bit more complicated.
That's certainly true. I mean, so the general point is a really good one, that that the more you try to kind of add hard constraints to the formulation, the more challenging the optimization becomes. And it's not like a law of nature, but it's often the case. Um, so the first comment on that is just that these are reasonably easy to train. So the constraints on the particle model don't really constrict us very much. And then, the total number of iterations and the training time is comparable. It kind of like sort of 4 to 10 hours across all of the cases that you saw here, with a
Okay.
single GPU. And it's not a state-of-the-art GPU. It's like a 4090 or something like that. So, um, but yeah, I mean, you could imagine being in situations where that would just be intolerable. Like you'd get an optimization that was hard enough that you didn't you either just were not able to approach a reasonable optimum, or it took too long. And so then in either of those cases, you should do something else.
Okay. Oh
Yeah.
no, but as I said, in your case it says 10 hours. That's more than reasonable. That's quite cool. I thought that since you were like doing this integration at every step for every single particle, that would be a bit more expensive.
That one took up to 20 hours. So I'm saying
Oh, okay.
and yeah, so, but that was also a 3090. I mean, so yeah, it depends. I don't know if you guys have a bunch of A4s or something, then maybe, or like A100s rather. I mean, then you might be in a different situation. It depends on what kind of resources that you have available to train. And yeah, and it's going to be very problem specific as to the degree to which that optimization becomes intolerable or not a big deal.
Okay. Yep. Yeah. Also, in that optimization, usually, for example, when you do reconstructions again, it kind of like works because then the data is kind of telling you, it's not letting your model do some crazy things, right? But again, when you try to infer things, for example, there were some hard constraints that I could not use in my models because
Mhm.
when you're trying to infer hidden things, and then it's like you have you have more freedom, right? Your model can go to many other places, and then if you try to constrain things, then it becomes harder to learn hidden fields. And that was leading to my next question, which like, did you try something like inferring hidden fields, like you have, I don't know, velocity in 2D, you want to infer the third component, or you have things like that, or
Yeah, so
temperature
all
from.
the pressure fields are inferred, right? So there's no data about pressure in any of these cases. And then in the supersonic flow, the pressure. So here we're plotting, so density and pressure. Obviously, we've actually parameterized this in terms of a total energy field, and we're just computing pressure. So those would be the fields we inferred here. We do a lot of work with the quantitative Schlerin methods where we would infer, I mean, which is again something that has been done in the Crunch lab, but we infer, velocity, pressure, and velocity, pressure, total energy, or sorry, velocity and total energy from a measurement of density, essentially. In all of those problems, we haven't encountered a huge issue with the latent fields. I think the cases where it was worst is if we were measuring like a passive scalar and then trying to infer velocity. That was pretty sensitive. If you have a low Schmidt number flow and you have a measurement of the scalar, then we found it really challenging to get anything good out of that for complex flows.
Okay, that's nice. But in general, I really like your work. It was really interesting. Thank you so much for sharing
Thank
with that. Okay, that was my question.
Okay. So I have two questions. First of all, excellent talk. Your examples were really great and carefully chosen to highlight the complexities of this, which we have been also struggling and working on this for some time. One of these issues that you actually addressed was downsampling. And because particle tracking velocity, PTV is good, but you need a lot of particles. And you saw you went down to 4 times. In the turbulent jet that we did with the LaVision, we tried to go down, instead of 16,000 vectors per snapshot, particles, we went down to 128. So we have severe, and we still were able to reconstruct the potential core, the breakdown. We missed some of the ribs in the streamwise vorticity and so on. But we were able to downsample both in space and time dramatically, which means equivalently means that you can scale up the system, right? For the same number of particles, you can scale up to, instead of millimeters, to meters and so on, like in what the project that we're doing with Mercedes with Formula One of the Lewis Hamilton car. So the question I have for you for the technique is, in the conventional method, we use the conventional method. We don't know how accurate we were, but anyway, you could get something. If you downsample severely, you cannot use the NIPA method, right? You cannot use the, but maybe it's still the inertial particle could be a good idea. The no slip boundary condition could be a good idea, right?
Yeah, certainly. I mean, I also think that, right. I mean, in cases where you know the characteristics of the particle quite well, I think that it would be beneficial to include that. I think I think the thing that motivates the question is what we're really interested in my group, which is that at some limit, it's just a hopeless problem. Like if I have a single particle, I can't do very much with that. If I have a continuum of particles, it's a trivial problem. So you've got a transition from a well-posed problem to an ill-posed problem. And the question is, at what point does that occur? And it will be a different point if you lack information about the particle dynamics versus if you have full information about the particle dynamics in terms of the Stokes number of the particles, for instance. And so, we're kind of working on the assumption that it's going to be related to the intrinsic degrees of freedom of the flow. So maybe use some manifold geometry and some modeling from the dynamical systems community to understand, well, maybe there are like low dimensional descriptions of this flow, and then these particle clouds kind of, if you consider those as observations of the system in a latent space, there might be, ways to grasp onto the trajectory with very little information. Understanding that, like projection of a particle, like sparse particle measurements into that latent space.
I think there is something like that. I don't know if my former postdoc, Sam Babai, who is at Pittsburgh, just yesterday showed me how, I mean, in combustion, for example, that all different species are transported by the same velocity. So that has some sparsity. If you're in latent space, you can see huge sparsity because they're all particles. All species are transported by the same velocity field. Therefore, there is a, but yeah, that's a tough problem. And where is exactly this downsampling in space-time so that we can, now another question is PIV versus PTV. if you have PIV, the problems are, if you have data from a PIV window, of course, it's a different problem, but if you embed the PIV window,
Yep.
it could be 2D or 3D, are the problems less, right? You cannot cover all the space, but the space that you cover, then are there any problems there? You see any problems?
So with PIV, I think in 2D PIV is really excellent. And so actually we have a talk at APS where we're going to discuss a neural optical flow technique where we take the image warping operator and we embed it in our data loss. So then the neural net warps the images and then you're just trying to get the neural net to match the two particle images instead of doing cross correlation or another optical flow method. But the challenge for PIV is really when you go to 3 dimensions. And the problem there is that you have to reconstruct the particle field before you can do any sort of optical flow analysis. And the reconstruction is, it's a very ill-posed problem. You have 4 cameras at the absolute most. You'd have like 12 cameras. You've got hundreds of thousands of particles. And if you're trying, and the way that TomoPIV works as opposed to Lagrangian particle tracking is that instead of localizing the particles and then trying to optimize those exact positions, you're reconstructing an Eulerian particle intensity field. And your degrees of freedom are massive. It's much larger than the number of particles that you've got. And so you have all sorts of heuristic algorithms to try to reconstruct that 3D intensity field, but you get really big errors. And those errors are not nice. They're not like Gaussian, uniformly distributed, et cetera. And so the people call them ghost particles. And so then if I've got ghost particles in my 3D tomogram, and I'm trying to use that as a method to advect or to deduce the velocity field, that's going to introduce a lot of bias into my estimate. So you'd either, I think there's 2 ways of dealing with it. One is that if you develop for a given set of camera arrangements, if you developed a data loss that did an appropriate discounting for the attributes of the ghost particles for that configuration, that would be one way of probably dealing with TomoPIV data quite well. Or you could, I think, something similar to AIV, what you guys did, if you were to parameterize like a particle intensity field and then just advect the particle intensity field and try to do an implicit reconstruction that way, I think that's a possibility. But the Lagrangian particle tracking algorithms are so good now that I would say until you've got very, very dense particle fields, you're much better off just getting each particle.
Okay. All right. Yeah, thank you very much, Sam. It was a great treat today.
Thank you.
Friday lunch. Thank you.
Thank you. Do we have any other questions? I don't think so. Yeah. So it's time to close the session. Thank you for your time and your great talk. Thank you everybody for joining us today. Have a great weekend ahead. Bye.